Good evening, everyone. Welcome to the 56th Annual Jansky Lecture. I'm Trish Henning. I'm the NRAO Assistant Director for New Mexico Operations. The Jansky Lecture is a distinguished lecture series established by the trustees of Associated Universities Incorporated and the National Radio Astronomy Observatory to recognize outstanding contributions to the advancement of radio astronomy. Carl Jansky was the first person to detect cosmic radio waves in 1932, and we named the lecture series after him. And we are delighted to have some of the Jansky family in attendance tonight. There is grandson Greg Jansky in attendance, as well as niece Marianne Edwards. Thank you both so much for joining us this evening. Tonight's lecture is entitled Jets from Stars in the Making by Professor Luis Rodríguez. Professor Rodríguez is being honored for his significant contributions to our understanding of star formation and X-ray emitting binary star systems. His distinguished career as a researcher and as an educator and popularizer of astronomy, as well as a mentor to an entire generation of radio astronomers. Professor Rodríguez earned his Bachelor's of Science in Physics from the National University of Mexico. He received his PhD in astronomy from Harvard University, and he received the Trumpler Award of the Astronomical Society of the Pacific, which is given annually to a PhD recipient whose thesis is judged particularly significant to astronomy. Some of his career highlights are he co-discovered outflows from star-forming regions and contributed substantially to the current paradigm of star formation. He co-discovered the first microquasars in the Milky Way, small black holes which are nearby and smaller analogs to the quasars that lie at the hearts of distant galaxies. He's founding director of the Institute of Radio Astronomy and Astrophysics at UNAM. And as UNAM professor, has directed 28 student theses and authored more than 500 scientific publications. With a Mexican government grant, he made an enormous contribution to NRAO, equipping the VALA with its first 43 gigahertz receivers, enabling imaging of dust emission from protoplanetary disks around young stars. He's currently Professor Emeritus of UNAM's Institute of Radio Astronomy and Astrophysics and coordinator of Mesoamerican Center for Theoretical Physics in Chiapas, Mexico. And he is working with NRAO to select antenna locations in Mexico for the proposed NGVLA. He has received the Mexican Award of Sciences, the most important recognition for a researcher in that country. And he's also received the AAS, the American Astronomical Society, Bruno Rossi Prize with Felix Mirabel for their work on microquasars. He's only one of 40 members of Mexico's National College, which brings together the country's foremost scientists and artists. He is a foreign member of the United States National Academy of Sciences and the Spanish Royal Society of Exact, Physical, and Natural Sciences. AUI and NRAO are delighted to have a scientist of Professor Rodríguez's stature for the 2021 Jansky Lecture. And I'm sorry I can't be with you in person, Luis, but let me award you this plaque. if you have, I don't know if you've got it there. You can show
Thank
folks.
You very much.
There it is. Thank you so very much for giving us this Jansky lecture this year. And so Professor Rodríguez will take over and give the lecture. I'd also say to everybody in the audience, if you have questions as we go along, please feel free to type them into the Q&A box at the bottom of your Zoom screen. And we'll keep an eye on those, and we will pose and answer questions at the end of the talk. So thank you very much. I will now hand it over to you.
Teresa, thank you very much for your kind presentation. And also, thanks a lot to Nikki, Karen, Amy, and Izzy for organizing all this and allowing me to give the lecture virtually. I'm also very thankful to the Jansky lecture committee for having selected me from I'm sure, a list of very distinguished colleagues. And I'm also always very thankful to NRAO. I'm happy to do anything with NRAO, this exemplary institution that has allowed thousands of astronomers, not only in the US, but in the rest of the world, to make a career, a productive career in astronomy. I'm also very happy to hear that we have members of the Jansky family with us. Unfortunately, most of us didn't get to know Carl Jansky because unfortunately he died so young, but we remember him every day. The upgraded version of the VLA is called the Jansky VLA. The unit we use to measure the energy from radio sources is called the Jansky. So that puts Carl Jansky, next to Ampere and next to Volta and all these great scientists of the past that made important and basic discoveries. So, well, thank you to all of you. And let me go and talk about this topic that has taken a lot of my research time of me and many other colleagues. And this is the so-called radio jets. And what are these objects? Well, in short, it's the finding that young stars, the stars that are just still accreting gas and becoming bigger and bigger until their mass allows them to start having thermonuclear reactions and become a real star, they happen to eject into the interstellar medium these flows of collimated gas. This came as a surprise because until 1980, everybody thought that the formation of stars was a process in which motions were of infall. That is, after all, we were trying to make a protostar grow in mass. So the way of doing this was, of course, managing to, in the models, to get mass that fell into the star. But when people started to study the process, to their surprise, the first thing we found was gas that was coming out of the star. And this created a lot of confusion and until we finally understood that actually both infall and outflow motions are present in the formation of stars, and both are indispensable components of the process. Well, there are two recent reviews on this topic. One is by Anglada et al., and the other focusing on radio results, and the other is by Rayan Ferreira, focusing on facilities, new facilities, and on models, and on optical and infrared observations. So if you really want to get acquainted with the topic, you should go to these two reviews. Let me tell you about something that these things that happen to you that you remember as if they happened yesterday, but this happened more than 43 years ago. And that was my first visit to the VLA site that I did with Jean Moran, my teacher and tutor in Harvard. And in June of 1978, Jean took me to the VLA in a project. And he told me, well, this instrument is going to be important in the next few decades, so it will be good for you to learn how to use it and to understand what it does. And sure, I say, let's go. And we flew to Albuquerque and did the usual trip. And when we got to the site, it was still 1978. The array wasn't officially inaugurated, so there were only 10 elements in the array of the 27 or 28, if you want to take into account all of the array elements present. And still, with those 10 elements, the VLA was already the most powerful interferometer in the world, and you could do a lot of things. And we went there, Jim Moran and I, to explore in the radio continuum the surroundings of these mysterious sources that were called the Herbicar Objects. We were trying to understand what they were, what was powering them. All this was a mystery in those remote days. And well, let me go a little further back. Back in the 1950s, this new type of nebula was discovered. This is a negative image of the region. And to the north, you see a very well-known reflection nebula, NGC 1999. Reflection nebula, it means that it is the dust in the cloud is just reflecting to us the emission from the star. So we know that there is a star in there. And then more to the center of the image, you have a mark HH1 and HH2. This is the way the objects were started to be known from the discoveries George Herbig and Guillermo Haro as HH objects. And what happened in those years is that George Herbig, then a young astronomer that had an extremely distinguished career over the years, he lived to an old age, and he remained productive over, I don't know, 60 or 70 years. And he published a paper in 1951 where he reported that he had seen two nebular objects that were remarkable in their spectrum, and that he couldn't relate to previously known nebulosities. This is an image of George at those times. And the next year, a Mexican astronomer, Guillermo Haro, also published a note saying that he had been working on these same two nebula, and again emphasizing how strange they were and how unusual they were. They were a new kind of nebula, and the objects became to be known as Herbicar Objects in honor of both discoverers that did this independently. Although over the years, Herbig and Guillermo Haro did publish and did collaborate over later in a number of papers. Well, the problem with these objects was that the spectra was unlike that of other known nebula. So it deserved like a new category. But even more disturbing was that they didn't seem to have an exciting star. You know, a nebula is emitting light, is losing energy, and that energy has to be coming from something. And what happens is that that something is a star, but in here a star was not detected, and this was quite a problem. Over the years, papers were published that had clues on the nature of the HH objects, and but we really didn't understood what was happening until some 30 years after their discovery. In 1958, for example, Don Osterberg, another really distinguished and very clever American astronomer, noted that near a young star, T Tauri, a prototype of young stars, there was a nebula that was called Burnham's Nebula, and he studied the spectrum of the nebula, and it didn't seem to be photoionized. That is, something else was exciting and making this nebula bright, and he came to the conclusion that the most likely mechanism was that the stars have wings. They are losing not only light or photons, but also particles. And these particles can shock the surrounding gas and excited it. And he proposed that this object that has similarities with the Herbicar objects was being excited not by photons, that was the usual way, but by a flow of particles. Over the years, several milestones followed. Haro himself and Minkowski in 1960 published a paper saying that we don't find the stars inside the HH objects. We don't know how they keep emitting light. Herbig followed the objects over the years. he obtained plates that, as we will see, became very important. And notice that they were variable on time scales of years. That is, some of them will become brighter, some will become weaker, some will disappear, new ones will appear. So they were variable in a few years. Steve Strom and his collaborators proposed at the point that the Herbicar objects could be reflection nebula, because that way he could put the star away from the Herbicar objects and say that the light was somehow illuminating the cloud and being reflected to us. But the nebulae were studied and they were not reflection nebula. Key paper came in 1975 when Schwartz revised the spectrum of these HH objects, and he came to the conclusion that if they look like anything, they look like old supernova. Supernova, as we know, are these massive stars that explode. At the beginning, the ejecta is moving at tens of thousands of kilometers, and they produce a certain spectrum when they shock gas in the surroundings. But as they age, the gas moves slower. And when it gets to be only a few hundreds of kilometers per second, they have a characteristic spectrum. And that was similar to the HH object. So Schwartz said that maybe shocks of moderate velocity, by moderate meaning hundreds of kilometers per second, could be exciting these HH objects. In 1980, Ron Snell and myself, with Paul Ho and again Jim Moran, we were collaborating a lot in those years. In the case of us, we were using the Kitt Peak radio telescope, and we detected this phenomenon, also Ron Snell and his group, of CO outflows. It turned out to be that in clouds where you were expecting all the gas to be quiescent and showing very little motion. Also, this was another misconception. It turned out to be that where you look at the gas in the surroundings of a young star, you would find a region approaching you and a region receding from you. You will find blue shifted and red shifted lobes of gas, and something had to be pushing that. And also you found that in the blue shifted so-called lobes, in those regions that were coming to you, you could also find superposed to the molecular gas Herbicar objects. This also became to be very important because it was telling us that Herbicar objects had to do with flows of particles. But again, the really key moment came when George Herbig, again himself, gives a talk in an AAS astronomical, American Astronomical Society meeting entitled The Large Motions of HH1 and 2. And he, on this unusual, he shows a movie. In those days, now it's all different and everybody shows videos and animations. But in those days, nobody showed this. So he came with a movie and it was a struggle to actually project it. And what he did in that movie was to show us images he had taken of the Herbicar objects 1 and 2, where you could see the HH objects were separating with time. This came as a surprise. And here is the blinking, you can see the blinking of 2 images, and you see how the objects are receding from a point in between them. This was a key picture. Everybody that was in the meeting understood that the Herbicar objects were something different, were objects that were moving in the sky, that they were being powered by some sort of collimated outflow. And a lot of the interest then became in finding where was the star that produced this. Herbig and his colleague Burton Jones published in 1981 a paper with the results. And this is the main graph of the paper, a graph that shows HH1 and HH2. And these objects have different condensations, and those arrows indicate the motion of the objects for a period of 100 years. And obviously they are sort of receding from something in between. At the point, a a star that can be seen in the optical, discovered by Cohen and Schwartz and called the Cohen-Schwartz star, was believed to be probably the object that was producing the Herbicar objects. But things didn't quite fit, and we decided that it was worthwhile to search this region using the Very Large Array. The argument was that maybe it was a young star that was surrounded by a lot of gas and dust, and you just couldn't see in the optical or even in the infrared. And hopefully the radio waves, if this source had the radio waves, you will escape from the envelope, and you would be able to detect them in Earth. So this result of Herbig and Jones told us that HH objects were not independent objects, in particular 1 and 2, but they were part of a system that was being powered by probably by a single object. All this is obvious now, but at that time it was really came quite as a surprise. So, you know, over the years, people have studied Herbicar objects, and this is a beautiful movie made by Pat Hartigan of Herbicar #1. And let me show it to you. Just beautiful. You can see how the object is moving towards up to the right, and here it goes again. And of course, the objects have been studied exhaustively since then. Well, so a group of us decided that it was a good idea to use the Very Large Array, which by then was completed. We're talking of the mid-1980s. It was completed, and it was working in a fantastic way. And we got time to look for radio emission from something in between the Herbicar objects. We were, we were hopeful that we were going to detect something, but based on two interesting papers that were published by Biegin, Cohen, Schwartz a couple of years before, in 1982 and 1984, in which they found also a surprising result. Low mass stars are cold, relatively cold, a few thousand degrees, so they don't produce high energy photons that could ionize the surrounding medium, and you don't expect any photoionized gas, and this is correct. However, when they started studying a number of young stars, they found that there were radio sources. Over time, the reason became clear. There were actually two mechanisms. On the left, I have a star that is emitting because the surroundings of the star have magnetic fields and have relativistic electrons, and emit by a process that is called gyrosynchrotron. And these are called non-thermal sources because the mechanism is classified as a non-thermal mechanism. And this has become a really important topic on its own. These stars are ideal because they are so compact, are ideal to do very long baseline observations and do exquisite astrometry. And for example, my colleague in Mexico, Laurent Loanard, has this big program where they have measured many of these stars, and they have found their motions and their distances with unbelievable accuracy. But what was most interesting is in the right part of this plot, and it is that these young stars, some of them seem to be associated with thermal emission coming from gas that is ionized. And we didn't know how it was ionized by then, but we knew that they emitted, and they will show an elongated morphology, and this elongated morphology will align with outflows and with Herbicar objects. So all this gave us confidence that something was going to be found in between the Herbicar objects. And that was indeed the case. Between HH1 and 2, so right in the middle, there was this radio source that is shown on the right part of the slide. On the left, we have an image from the Herbig and Jones paper. On the right, we have the radio VLA source that is called VLA1. It's very small, it's in between the two HH objects, and it shows an elongation along the axis of the HH objects themselves. And this was published in collaboration with Steve Pravdo and his colleagues. This is a modern picture of the Herbicar Objects 1 and 2, where we see, this is of course made with the Hubble Space Telescope, and we see exquisite detail in the Herbicar Objects, but still the source in the middle cannot be detected. It's just so obscure that practically all the information we have from it, it comes from the radio and from the infrared. What we do manage to see is a jet that is displaced a little from the position of the star that points to HH1, and actually that's the phenomenon that powers and gives energy to HH1. And that's why Herbig-Haro objects don't have an embedded star, because the star that is exciting them is displaced, is some other place of the region. Alex Draga has done an interesting sociological research. So he asked himself, how many significant papers have been published on these two Herbig-Haro objects, the first discovered the archetype of the class? And he got this result, which is that on the horizontal axis, we have the year of publication, and on the vertical axis, the number of significant publications that, according to him, came with a contribution. And what we see is that from 1950 to 1980, not much happens. One paper or two papers are published. And then from 1980 to 2000, we get several contributions per year on the topic, and the knowledge of Herbicar objects advances a lot. Now, after 2000, the number of significant papers has decreased, but that's the way science works, right? We have 10, 20 years that we usually need to understand a phenomenon, and then the interest moves to other objects. And this science is a little cruel, but that's the way it is. This knowledge came to be crucial for establishing what is known as the paradigm of star formation for low mass stars, for stars similar to the sun. And the idea is shown here in these 5 cartoons. The first one is that we have one of these large molecular clouds that have hundreds or thousands or tens of thousands of solar masses. So you can form a lot of stars from those clouds. A chunk of the cloud loses support and starts to condense. And since you have angular momentum, you have rotation, what you form is a core surrounded by a rotating structure. And the jet phenomenon appears. At the same time that you are accreting gas from the disk, the star has a mechanism that we will see later to produce jets that fly out of the surroundings of the star and shock the gas, produce the Herbicar objects, also entrain molecular gas and accelerate molecular gas, and produce the phenomenon of the bipolar molecular outflows. But over the years, this rotating structure is very important. It's the protoplanetary disk. It's the structure from where planets will form. And slowly over, not that slowly, over time scales of 1 million years or so, that disk transforms into planets. And then, since the disk is the one that powers, let's say, the jet, the disk starts transforming into planets, the jet phenomenon, the outflow phenomenon disappear, and we end with something that looks very much like our solar system. And this paradigm is still pretty much accepted, and it has guided our research. It was developed by Frank Chu, Fred Adams, and Susana Lizano back in the mid-1980s. And indeed, with Bo Rayport, we started a program with the VLA, and basically where we had HH objects, we will go and do an observation and find these sources. Here is another example, the system HH111. This on the left, we have a Spitzer image of infrared image combining colors, and we see the beautiful jets coming out from the central region. And when we go to the VALA and observe the region, in the center, we find a jet. We find this on the right side, you can see this source, elongated source that points to the Herbicarol objects, and that when we study them, we find that that's ionized gas coming out from the star, moving at velocities of hundreds of kilometers per second, and producing the Herbicarol objects, and also producing the molecular outflows, the bipolar molecular outflows, because the jets entrain, as I said, and accelerate gas in the surrounding medium. People keeps working on Herbicarol objects, and a few years ago we had this paper by Bo Raper where he reported the HH objects 1,000, and now the number must be somewhere around 1,200 HH objects or so. And actually, when you go to a cloud that has star formation, you find that the cloud is peppered with Herbicarol objects, which is the images we have back in the 1980s were not good enough for this. And to the bottom of this image, you can see Herbicarol 1 and 2, which are very bright. And that's why Herbig and Haro could discover them back in the 1950s, but they didn't see all the other HH objects. Now, with these fantastic images that you can get with the Hubble Space Telescope and with other extremely powerful optical and infrared telescopes, you see that the region is filled with Herbicarol objects that, of course, are telling us that there is a young star in the making somewhere around them. Actually, there are Herbicarol objects that you can only see in the radio, because again, we're talking of regions of great obscuration, and Herbicarol 1 and 2, because of their geometry, we are lucky to be able to detect them in the optical. But here is an object in the region known as W75 North, work done by Carrasco Gonzalez, a colleague also in Mexico, where he has images over the years. And at the center of the image, we see what we think is the jet. And to the north, there is a Herbicarol object, probably, that is not moving. But then to the south, we see a faint region of emission. A few years later, the region has become stronger. And a few years later, it has moved to the south with velocities similar to those observed for optical Herbicarol objects. So this will be radio Herbicarol objects, objects that you cannot see in the optical, and you cannot call really Herbicarol objects, because as Bo Raper always tells me, you cannot call them Herbicarol objects because the classification is from the optical, so you have to call them radio Herbicarol objects. So they are radio Herbicarol objects. Another thing that we understood from basic physics is why Herbicarol objects move, while, for example, the gas in the ionized region doesn't move that much. And the reason is that photons have their momentum to energy ratio, that is the ratio of the momentum to the energy, is very small. So photons are good in transferring energy, but they are not good at pushing things. In contrast, particles have a large momentum to energy ratio, and they are good at transmitting energy, but they are also good at transmitting momentum, which means that they will push things. And that's why Herbicarol objects move, while other types of nebula don't move much or at all. Well, over the years, a lot of the interest in Herbicarol objects shifted to these radio jets that you could do best with the VLA, also with Merlin, the British Interferometer, also with ATCA, the Australian array. And here is a panel of some of the brightest objects, and you see always an elongated source at the center. Sometimes you're looking and you see in the radio the two Herbicar objects, and you can study proper motions, and you can try to understand why is this photoionization, no, excuse me, ionization produced is not photoionization, is an ionization due to shocks, to the fact that the jets that come from the young star system shock against surrounding gas or shock even inside themselves and get ionized and emit radio waves. And it is thanks to that we can detect them. Over the years, the work of several groups, we have been able to characterize these radio jets. We call them thermal to distinguish them from the most famous, more famous non-thermal radio jets that emanate from black holes of all masses, from quasars, active galaxies, and also from black holes that come from the death of a star that also can produce these radio jets, something that was discovered also with the VALA. That happened in the 1990s. So these thermal radio jets that emit via the free process, which is a thermal process, as it is called, they are elongated. We know that they are collimated on pretty small scales. They are associated with both high and low luminosity objects. This is interesting because the phenomenon could be restricted to low mass stars or to high mass stars. No, it seems to be a very robust phenomenon that appears over young stars of all masses. And the jet is aligned in general with the outflow. Sometimes it is not. And they are unfortunately weak sources. They have fluxes around a milli-Jansky. And this means that you have to invest time to do them well. They have motions in the jet of the order of a few 100 kilometers per second to a few thousands. Something very interesting is that when you look at the jet, at the radio jet, you see gas that was next to the star a few years ago, and it's just starting to go away. In contrast, when you see the Herbicar objects or the molecular outflow, you see stuff that was ejected hundreds or thousands of years in the past. So you can study the ejection at different epochs by comparing these two scales. And we know that the ionization starts close to the star. And there is a model published by Reynolds back in 1986 that allows you to interpret these objects very well as collimated jets that emit this mechanism that is called free radiation. As I said, this is a very robust phenomenon. We find that there are jets not in the so-called main sequence. I mean, the sun, for example, doesn't have jets anymore. But in all the phase of a star formation, where we're talking of a few million years, the star has jet phenomena. And this can be seen on the left with the so-called class 0 object, the youngest protostars that we can find, they have jets. And this phenomenon becomes progressively weaker. And on the right, we have a star, AB Auriga, which already has a transitional disk. Its disk is already becoming planets. And the phenomenon of the outflow is becoming weaker, but it is still detectable. So this is a pretty robust phenomenon that appears, as I said, in stars of all masses and also over a good part of the star formation stage epoch. They, as I say, they are also observed for young stars of all masses. On the left, we have a source that has the luminosity of an old star. It's a very luminous young star. And then we see this, of course, in many solar type young stars, and even in stars that that have so little mass that they are not really stars. They don't manage to burn hydrogen ever, and they are the famous brown dwarfs, sources that are sort of between planets and stars. And these sources also have outflow phenomena. And I'm showing examples of the work of Lee and Palau that show these outflows coming from these extremely faint, extremely low mass objects that, as I said, don't even qualify as stars. They are in the substellar regime. There are correlations that help us understand what's going on. On this correlation from a paper by Palau, on the horizontal axis, we have the bolometric luminosity, the total luminosity of the source. And on the vertical axis, we have how much flux is being injected by the jets in the medium. And we see a correlation. The more luminous the star, the stronger the momentum is, the rate of momentum it injects into the surrounding medium. Another very interesting thing is that we can study extremely young objects that are very obscure. The younger the object, the more massive is the envelope that surrounds it, and the more dust you have around, and the harder it is to see at wavelengths other than radio. So we have found that many of these sources that were believed to be single actually happen to be binaries or even multiples. And here's an example that we have studied a lot, which when you see in the radio, you discover that it is a binary separated by a few tens of astronomical units. This issue of binarity is best illustrated by BLA1, the source that I talk about that excites the HS objects 1 and 2. And in this beautiful image by Tobin, you can see the jet. But then there is that other faint source, which is a companion star. And that star is interacting with BLA1 and may help understand why ejection seems to be very strong for epochs and then come down, and there is another ejection epoch. And this could be related to a binary system with an eccentric orbit. And every time the two stars get close, this could excite accretion from the disk and excite the ejection. So we have been learning a lot from this and other objects. We can measure the proper motion. Sometimes we're lucky and there are knots in the jet and we can see the knots moving. And as I said, we get velocities of hundreds of kilometers per second for low mass stars, up to thousands of kilometers per second for high mass stars. There is also a correlation between the velocity of the jet and the mass of the star. Well, all this time we have been talking of thermal emission. Well, it turns out to be that when you study these things in detail, you find that the core of the jet, the central region, is generally thermal. But as you study the jets that are flowing into the interstellar medium, you have shocks there. And when you have shocks, you can accelerate electrons to relativistic velocities, and you can produce synchrotron emission, an example of non-thermal radiation. So now we are more careful when we talk. We say that, all this is thermal. No, the cores are thermal in general, but the jets can well have a non-thermal mechanism. That's, on a way, good, because you can learn about magnetic fields in the jets, because the synchrotron emission is a result of relativistic electrons and magnetic fields. And you can say things about the magnetic field that, as we will see, is very important to produce the jets. One of the key problems in astrophysics and actually in physics is how are these jets accelerated and collimated? We have been talking that there are these flows of gas that are very narrow, very well collimated, moving at large velocities. It's a very important unsolved problem because jets are very common. As I said, we see them in protostars, we see them in acritic black holes of all masses, we see them even in some planetary nebula, a different type of sources. We have as a reference the so-called Blanton mechanism, where the rotation of the disk powers via magnetic fields, gas, and launches and collimates jets. And I will show you a little more about these models. You need extraordinary angular resolution and sensitivity to study this, because all this is happening very close to the star. And you have to go with very high angular resolution. Things have been improving. Merlin, the British interferometer, has produced images that show that collimation, it happens very close, within a few astronomical units of the star, but the sensitivity is not enough. So we are all really hoping for the next generation VLA that will provide this enormous angular resolution, but at the same time, the sensitivity you need to detect these relatively faint sources. The outflows are studied a lot. In molecular gas, you actually see in some studies, like the two examples I showed here, you study the molecular gas that is going away from the star, and you make a cut perpendicular to the axis, and you find that there is evidence that the jets are rotating. And this is good, the molecular jets, I mean. And this is good because supposedly they are coming from a rotating disk, and they should show rotation. But most people will be happier if we could prove that very close to the star. At these scales that we see here, the jets may have interacted with gas, and we may be having something that is fooling us into believing it is rotation, although rotation seems to be the best explanation. And again, this is another reason to go very close to the star and try to see if the jets are rotating as they emanate from the system. Well, I have talked a lot about Blanford and Payne. Roger Blanford got the honor of the Jansky lecture a few years ago, and he was extremely happy with this, as myself. And his model is basically that you have these disks that have a lot of rotational energy around the star. And what happens is that if you have a magnetic field that is entrained in the disk, the magnetic field also rotates and accelerates gas at high velocities. And then the same magnetic field wraps around the gas and collimates it. And this is a beautiful theoretical result, but we need extraordinarily good and high resolution and sensitive observations to really prove it is correct and I mean, put this important problem to rest. Another thing that is coming, will come also again with the next generation VLA, is that the jet, as I said, is a thermal emission, ionized gas that produces free emission, but also it will produce the so-called recombination lines that are produced as the electron cascades in the levels of hydrogen. And this is weak, but again, if you make the numbers, you will be able to see it with the next generation VLA. There are now some tentative detections, but it is not clear what is really going on. And this is something that, again, it will get much better in the near future. Well, in the same way that HH objects lose protagonism as jets became important, now jets have sort of lost relevance with the study of disks. Disks are just now such a hot topic. ALMA, the Atacama Large Millimeter Array, has produced these astounding images of disks that show disks at various stages of evolution, and these that appear to be transforming into planets, the presence of gaps that are interpreted as that the planet formed there. And this is all extremely exciting. One thing important to remember is that when you observe a disk, the inner few astronomical units are very important because terrestrial planets are supposed to form there, and jets are also present there, and the emission of both are going to be relevant. And we need to understand jets to understand disks and vice versa. We need to understand disks and to disentangle the two mechanisms and come with a better understanding. And this is exemplified with the images made with the BLA at 43 gigahertz at 7 millimeters by Carrasco Gonzalez. And in there, he has analyzed the inner emission of the classical HL tau. This is the prototype, and they are beautiful ALMA images. But as you go to the inner part, you find that at the ALMA wavelengths, the disk is optically thick. That means that you cannot see what's happening inside. And you have to go to the wavelengths of the Jansky BLA and to the wavelengths that the next generation BLA will have to penetrate that important region, that region where planets like the Earth are formed, and be able to see the jet and also see how is the disk behaving and separate these two phenomena. Now, of course, the next generation BLA, as I say, will change all these, will allow us to do all these things that we're just now dreaming about, and getting more and better information on jet acceleration and collimation, understanding the formation of planets very close to the star, and all these dreams will become a reality because now we know that the next generation BLA was very strongly backed by the decadal review, and these goals will be achieved in the future. And that's really fantastic because we will have another major step in the understanding of the phenomenon of star formation. Well, let me end here. And again, thank everybody at NRAO, the Jansky Lecture Committee, all our colleagues here. And I hope that you enjoy the talk, and I look forward to your questions. Thank you very much.
Thank you so much, Luis. That was an excellent, excellent lecture and gave us a slice of some of your very, very deep expertise. So very much appreciate your sharing that with us. It's really quite a story that goes back decades now. So thank you very much. So for the audience members, please do type your questions into the Q&A box. And let's see, we're getting congratulations in the box. So Luis, actually, I would make a comment that it seems to me, you've had 28 thesis students, PhD students over the years. There must be at least that many PhDs waiting for the NGVLA in this field, right? There must be.
Certainly, yes. There are actually hundreds of PhDs waiting for the next generation BLA, because we're talking of not only the US, but the rest of the world. So there is a tremendous expectation, and we're all looking forward to the completion of this instrument.
That's great. Okay, we do have a question popping up now in the chat. The first one is, why do we think that terrestrial planets form within a few AU of a star?
Right, that's an excellent question. We believe that the Jovian planets form away from the star, and it turns out to be that there are Jovian planets very close to the star. So the other thing can go the other way around. The thing is that most stars are sort of similar to the sun. And then if you want conditions, behind all this, of course, is the idea of finding another habitable place for us. which we're going to need in, I think 5,000, in 5 billion years, but we will need it. So there is a lot of interest in finding signals. So the logic behind is that many stars are like the sun, and if you want a planet with a reasonable temperature, it's going to be close. So the presumption is that they are there, at least the ones that are potentially habitable. But the person that asked the question is totally right. Now we know that all our preconceptions that all planetary systems are going to be copies of our planetary system are totally wrong. And there are all sorts of things. But the idea behind has a lot to do with habitability.
Great, thank you. Next question. Why do the jets stop? Why does the sun not have jets?
A great question. The thing is that the jets are fed by the disks. Once the disks disappear, there is not a continuum of gas that could feed the inner parts of the system and produce the jets. So the jets disappear with the disk. Let's say that they coexist, and actually there is like a symbiotic relation. Jets take away angular momentum that allows the gas to fall in the star. If you didn't have jets, the gas will remain rotating there forever, and you will never form a bigger star. But then the jets take away momentum, but at the same time get energy and momentum from the disk. But that's an excellent question. Somebody once asked me, where are the Herbicar objects of the sun? And the answer is that.
Yeah. The next question is quite closely related. Does the ejection of the jet material affect the evolution of the pre-planetary disk?
Yes, yes. Certainly in the inner parts, we know that the jets are coming from very close to the star. And there is all this discussion on whether they are coming from a region very, very inner that will not affect the immediately surrounding disk. But other models suggest that jets are also formed from material that is a little more remote. So again, to understand jets, the planets, you need to take into account jets and vice versa. No? So you need to understand both phenomena, and they are related. Now we sort of, what we understand is that the relation is in terms of energy and power in things, but the relation is probably deeper, and this will be discovered with better observations.
Great. I think I'm not seeing further questions. Other panelists can correct me if I've missed anything. What I'm seeing is lots of congratulations to you. And thanks for the excellent lecture. And so, we have a late breaking question. Here we go. Yes, magnetic field lines have been receiving attention recently, not just in jets, but also in very long distance galactic structures. What is your hunch about the role they play in both stellar and large scale structures?
Yes, they are very important in the Blanton and Payne model. Without magnetic fields, you cannot produce jets. Simply, there is no way of transferring this rotational energy of the disk to larger scales. And it is the magnetic fields, the ones that do this. And the same at larger scales, we know that there is a magnetic field threading the whole galaxy in an organized way. So magnetic fields are a key component. Usually when you take a course, the teacher leaves magnetic fields to the end because they are hard to deal with, but they are very important and are another component that we just can't ignore.
Right, great. And now another one. What is the relationship between the jet's orientation and the star's rotation?
Well, the idea is indeed that all these things will be aligned because the star is gaining its momentum from the material of the disk. So the star will be rotating and the axis of the star will be closely aligned to the jets and perpendicular to the plane of the disk. Now, in most cases, again, for this you need very high angular resolution to attack that problem, but that's what theory will tell you, that there is a lot of alignment because things are interrelated and they are not working on their own. They are all interrelated and they are strongly correlated.
Great, yes. You have a lot of interest in this talk. We have another question if you're willing to,
Sure,
answer another one. Okay. If the proto-solar disk had jets, can you speculate on how we might see evidence of the jets from Earth today?
Great question, great. Yeah, sort of like astronomy. Well, I think that the problem is that this has happened so far in the past that probably everything just has expanded and diluted. It's like, you know, a supernova. The first thousands of years, you see something fantastic, but as time goes by, the gas sort of mixes, and I think you lose track. But that's a great question. Maybe there is some way of finding this, right? It's like people now has been using Gaia, has been finding this evidence of these dwarf galaxies that came into our galaxy and, you know, leave stars with peculiar motions. Maybe we could study the surroundings of the sun and find the evidence of the jets. That's a great question.
Great, thank you. Another question, is it logical to assume the jets we see, the jets we see are what is not absorbed by the disk? I'm not quite sure I understand. Let's see, is it logical to assume the jets that we see are, okay, the jets that are observable have not been affected by the disk, I gather. I'm not quite sure I understand the question.
Right, maybe the person is thinking this issue that, you know, the radiation that an object produces, some of it is absorbed by the object, but we're seeing sort of the emission from the outer parts, so we do see them very well.
Yes, indeed. Good, thank you. And now I do believe we've caught up with the questions, lots of interest. So thank you so very, very much, Luis. On behalf of AUI and NRAO and the audience, I want to thank you for your excellent lecture and for your enormous contributions to the field. Thank you so much for sharing your expertise with us. I'd also like to thank the members of the Jansky family who were able to attend, and to the entire audience for spending your evening with us tonight. So thank you very much. Good night.
Thank you, Trish.